Welcome to this class, and we are discussing rate matching module. We discussed a part of it. We took one example wherein the code rate which was asked by the user was higher than the mother code rate which was generated by the LDPC encoder. Okay, and we'll take another example wherein the code rate which is asked by the user now is lower than the rate 1/3, which is the mother code rate. Okay, and we will see how this rate matching module works in this case. Okay, right. So how rate matching can reduce the rate also, that's the idea. Okay, so we saw how rate matching can increase the rate, and that happens by dropping the bits at the transmitter. Okay, we see how we'll see this now. Okay, and we'll discuss some of these modules if time permits in this class, otherwise in the next class. Okay, we'll discuss something called code block interleaving and what is concatenation and scrambling. Okay, that will happen in the next class. References are mentioned later in the slides, so we'll discuss that. Okay, so what we have seen until now is basically this. Again, I'm recapturing this so that we understand where we are. Okay, so transfer block comes here, transfer block CRC is appended, then the transfer block gets segmented. Okay, then and that segmented transfer block is called code block. To each code block CRC is appended. Then each of this segmented code block undergoes LDPC coding. Okay, output of that is at the rate 1/3, which is not the rate the user has asked. Then there is a block which is basically does the rate matching. Okay, which matches the rate to the matches rate 1/3 to the one which is asked by the user. Okay, followed by modulation. Okay, right. We'll see that some other modules also come in between. Okay, but this is what we have seen till now. Okay, and the reverse process of that, and we'll go through all of this in great detail. But this is there to make us understand how receiver actually works. Okay, right. So modulation, opposite of modulation, demodulation has to happen. Okay, right. And then this rate matching module. Okay, opposite of that. Okay, there is something called rate recovery. We'll see that in great detail, but I'll just jump the gun and tell you what is this module doing. Okay, so that this whole of this this receiver chain makes sense. Okay, now LDPC encoder works at the rate 1/3. So LDPC decoder is designed for that rate only. Okay, so LDPC decoder also works at rate 1/3. But the rate what is coming here, basically what is this? Is the rate which is asked by the user. Right, because what is this rate? This is, let's say, 0.6. You modulate it, you demodulate it, what will happen? You will get that rate back, 0.62. But the LDPC decoder is designed to operate at rate 1/3. Okay, so what is this called? So what will this module do? It will take this 0.6, it will map it back to 1/3. How is it done? We'll see later. Okay, right. So you can see some of the students say rate dematching, but it's actually nicer name is rate recovery. Okay, that you are recovering the rate, okay, which was asked by the user to one which is required by the decoder. This is always 1/3. Okay, right. This can be higher or lower, but this is always 1/3. Again, the same idea that you don't want to design 20 odd LDPC decoder for each of the rate which is defined in the standard. Okay, again the cost. Now, okay, so LDPC decoding, there was C=4 code blocks, correct? Okay, then each of them is getting decoded by the LDPC decoder. Then each of this code block has a CRC which gets validated. Okay, and all these code blocks are put together, they're concatenated, and then this is basically what will you get? You will get a transfer block, and at the end there will be this transfer block CRC. Gets validated, it's passed on to the MAC layer. Done. Otherwise, hybrid IRQ kicks in, we have discussed that. But this is the outline of the receiver. So this is now what we are going to see in this class is that this is rate 1 by 3. If the rate is lower here, what needs to be done? That's the idea, okay, right? And you'll see that we'll take another user allocation, okay, resource allocation, and work according to that, okay, because the reason is each of this MCS has its own rate, okay. Whatever MCS 16 we took, that's a predefined rate. You cannot reduce the rate there, okay. So you have to move to another MCS index where the rate is lower than 1 by 3, correct, okay. And easiest possible example is MCS 0, okay, right, that's the lowest possible rate. And what is this? The code rate is 120 by 1024, it's 0.1, right, lower than 0.3, correct. So it satisfies our requirement of understanding how will a rate matching module work for this case, okay. But MCS 0, what is the modulation? It is the 4 QAM is the modulation, okay, right. And how many PRBs are allocated to this user? I am taking some number n PRB is equal to 10, fine, okay. It can be 50, it can be 275 also, doesn't matter, okay, right. So depending on this n PRB, okay, the transfer block size is going to change because you have more resources. You will send a MAC will send a larger size transfer block, of course. So the transport block size is coupled to the number of PRBs which is allocated to the user and the MCS which is allocated to the user, okay. Once we see this formula which come much later, okay, you will see all these parameters being used in calculating the transfer block size, okay, right. Now, so the effective transfer block size which is sent by the MAC in this case is only 368 bits. Look at, we have come to the other extreme, okay, right. How many PRBs were there earlier? 70. What was the MCS index? 16, okay, and the transfer block size was running into thousands of bits, correct, okay. Now it is only hundreds of bits, and the reason is obvious. This user is in a poor SNR condition and has a low data rate requirement, fine. So, but what is going to happen now? As soon as it is, this transfer block comes to the physical layer, 24-bit TBCRC is attached, okay, right. Total number of coded block, we don't have to run the segmentation block here, okay. Without running itself, we know that how many segmented blocks will be there? There will be only 1, because it is much lesser than the number which is the 8448, okay, that is the number, okay, it's much lesser than that. Of course, like segmentation, it will go through the segmentation module, but segmentation module will not segment it, right. So, fine. Now, the output of this, the segmentation module, what is this? Total number of coded block is 1, 392. This needs to be encoded by the LDPC encoder, correct, and LDPC encoder can encode a certain selective sizes, right, which essentially means that encoder can only be of a particular length, right. If that length doesn't match, if this length doesn't match what the LDPC encoder can encode, what needs to be done there? One needs to append the filler bits, right, okay. So segmentation module is going to add that, even though it's not going to segment it, but it's going to append those filler bits. So segmentation module has its role, okay, of appending the filler bits, right, okay. So, and why are we doing it? Because we want to understand how rate matching is done in this case, but you have to go through this whole chain, fine. So you have to search for this minimum value of ZC, okay, this is this table, we did this exercise earlier also, and what is this minimum value of ZC? That KB into ZC should be equal to K, right, okay, which is greater than equal to K dash, correct. What is this? Like what is K dash? K dash is 392, okay. K dash is transfer block plus CRC without filler bits. K is K dash plus filler bits, right. So what is happening here? What is this number KB? KB is 22, correct. What is this number of systematic columns? That is fixed. Remember that this is what we learned in the last class. Okay, right? Do this math. You have to search through this. Write a small module to do this exercise in the segmentation module. Okay. So what is this? 22, and you will see that 18 is the ZC is the lifting size which satisfies this condition. Okay. What is coming out to be 396? What is this? That is ZC is the minimum number which makes sure that K is greater than equal to K dash. Okay. Right. So ZC is 18. 18 is somewhere sitting here. Okay. So it gives us 396. How many filler bits need to be appended? 4. Okay. 396 minus 392. Because LDPC encoder can encode only this size. Fine. Okay. Right. So filler bits are added to match to the suitable lifting size, and its number is 4. Fine. So what is happening here? So total of one code block. So what is the summary of this segmentation module here? C is equal to 1, which is of size K, which is 396 bits, with filler bit F is equal to 4. Correct? Okay. And what will be the output in this case? What will be the output length? N is equal to 66 ZC. Okay. Right? LDPC encode output for each segmented block. I have written NR, which is N. Okay. What is this? 66 into 118. Okay. 66 into 18, that is 118. Now you see the rate exactly here also. What will be the rate here? Rate will be K by N. What is this? 396 by 1188. Exactly 1 by 3. Okay. Mother code rate is always 1 by 3. Fine. LDPC encoder rate is 396 by 118, which is 1 by 3. Neatly done. Okay. Right? Fine. But the code rate asked by the user is 0.1. That's the problem we are trying to understand. And the design of rate matching module to handle that. Okay. Right? So how do you do it? Now again, we'll do the same exercise. So how many bits which can be transmitted for this 10 PRPs? That's the allocation which is done to this user. How many bits you can transmit? G. Total number you can transmit is G. And what is E? What is the difference between G and E? Let's recall. E is G by C. Right? E is basically the number of bits which you can transmit for each code block. G is the number of bits which you are allowed to transmit for all the code blocks. Correct? In this case, E will be equal to G because C is 1. Okay. We'll see that. But what is G? 10. How many resources? 10 PRBs. 162. Where is this coming from? Let's recall. Okay. How many? One PRB has how many resource elements? 12 into 14. Okay. That is 168 minus 6 for the pilot. That's what it's coming from. Okay. Right. So keep this in mind. I can, if the pilot increases or reduces, we can do that. Okay. Then correspondingly, this number will reduce. Okay. Because you are blocking certain extra subcarriers for the pilots. Right. Okay. What is the modulation being used here? Here is 4 QAM. Right. So how many bits you can transmit? 3240. Fine. Okay. Look at the difference now. Okay. How many bits you have generated? 1188. How many you are allowed to transmit? Right. 3240. Okay. Right. And so length of the rate matched code block E, which I said is G by C. So the total number of bits which you can transmit for this code block is 3240 because C is 1. Okay. Right. So before we go there, what is happening here? Okay, let's understand this. Rate is 1 by 3. Rate asked by user is 0.1, that is 1 by 10. Correct? Okay. Now for that rate, what does that mean? Okay, rate 1 by 10. For each message bit, you have to generate 9 more parity bits. But how many you are generating? Only 2. right? How will you match this? Okay, simple idea, read those bits, that's all. Okay, that's what we are going to see. Okay, right? So that's where the circular buffer will kick in. But before that, we have to calculate those RV indices also for the hybrid ARQ. That this K0 comes from that formula which I gave you in the last class. Okay, right? The same formula doesn't change, and that's, you'll get these 4 RV indices. Okay, because rate matching implements the hybrid ARQ also. Fine. Okay. So what's happening here? That's how this. See, what will the length of the circular buffer? Length of the circular buffer will be n, right? How much is that n? N is 1188, correct? Okay, so that you see this 1188. Okay. N is a circular buffer, and let's say you are transmitting RV0. How many bits you are allowed to transmit? 3240, right? What will this rate matching module do? So what is, it will start reading from here 1188, correct? It will see that it is still not finished 3240, go back and reread. Okay, that's where the circular buffering is used. Okay, but what is the idea here is, because you have generated lesser number of parity bits than what the user has asked for, okay, right, then you basically reread those bits. It's not the retransmitting, you reread those bits and transmit them again. In the same coded block, you transmit them again. This is not hybrid ARQ. Please keep in mind. Okay, this is only RV0. Okay, and why are we running upon this condition is because you have generated higher code rate than what the user has asked for. You have generated lesser number of parity bits than what the user has asked for. Correct? Okay, right, it's where it is. Okay, so we are actually done. Okay, so for taking this example, wherein like we understand that how do you generate a lower code rate from the higher code rate. Okay, right, again the idea is, why is it done like that? To reduce the implementation complexity. Fine. How is it actually done in the standard? That's what I am going to show you. So what we have done till now is basically we have understood how rate matching module can increase or reduce the rate, right? So recall the bit output of LDPC encoder is decoded as D. So this LDPC encoder is going to go into the rate matching module, right? So the bit input to the rate matching is therefore these bits. How many bits are going inside the rate matching module? What is the n? Correct? Okay, that's what it is, right? And how many will be read out, right? And see, the bit output of the rate matcher is denoted as E. Input is D, output is E. Okay, right? And it makes sense to, like, when you are coding it, you know, okay, it is A, B, C, D, E, F, G, H. That's how the input outputs are. Okay, it becomes very easy to remember that. Okay, it's all intentional. Okay, right? It is not given a fancy name. It can be as simple as that, right? Okay. So how many bits you are reading out? E for each code block. Okay. So this is the input and output, but I'll take you through how this rate matching module is actually defined in the standard, the instructions given to implementing this rate matching module. Okay, right? So let's see that. Okay, what is this? That's how it is given. I'm just like using exactly what is defined in the standard. As I am repeating myself, the idea of this course is to make students read the standard, understand how it is different from reading a book. There are no intuitive insights in the standard. Okay. The intuitive insights come by doing this kind of course wherein like somebody has already done it and they are able to tell. Books are also there, but they come much later. Okay, wherein like standard is defined, so there are these people like you who once do it, then they know how to read it. Okay, right? So what is happening? What are we denoting? Denoting this RVID. This is a redundancy version. Okay. And it can go from 0 to 3. Okay, and so this is a rate matching output sequence. How is it denoted? EK, that's how it is denoted. So I am reading the instruction. I have just copied the instructions which are given in the standard. Okay, is generated as follows. So you have to, from input is D. How will you generate E, which is the rate matched output from D? That's what this instructions will tell you. Okay. where K naught is given by table 4 point, this table, and I have shown you that table, how this K naught, that RV is calculated, right? K naught, K1, K2, K3 calculated, right? Okay. So based on this, you start reading from a particular RV ID, okay, 0, 1, 2, 3, okay. So what is happening? You see this, okay. So before we get into this, let me tell you one more thing, okay, that this, what is the job of rate matching module is also to remove these filler bits, okay, because filler bits are dummy bits, they are not transmitted, okay, right. And why were the filler bits added? Because we wanted LDPC encoder to work, correct, okay. You see this, so LDPC encoder has done its job, it has taken in the encoder input with the filler bits, okay, it has encoded it, okay, right. So, and this LDPC encoder is not going to change the position of these filler bits, okay, right, it does not change that. So, whatever was the position of the LDPC encoder bit, those bits are going to, the position is going to remain same, okay. So, you are going to reinsert those filler bits at the end of the LDPC encoder. We understand what I am saying here, okay. So, what is happening here? LDPC, like I did not show it here, okay. So, the LDPC encoder, there was this filler bits which were added. At the output of this LDPC encoder, there will be these filler bits whose position has not changed, okay. So, you will reinsert these filler bits, okay, right, and they will be different from 0 and 1, you give them any number -1, okay, right. So, what is happening here? So, J's index is a running index, will, okay. So, what is this? While K is less than E, how many bits you are supposed to be reading? K, E bits, okay, K is an index for that, right, okay. What happens? So, you see this, if this, you read, what is this D? What is D? D is the input to the rate matching module, correct, okay. What is K naught? K naught is the RV index, correct, okay. K naught is given by according to the RV ID. K naught is the starting point, okay. So, if K naught, for the first RV, what is the starting point? K naught is 0, correct, okay. So, what will happen here? K naught is 0 because you are transmitting first RV ID. J is, what is J set to? 0. What is mod NCB? That is the circular buffering. NCB is what? Is equal to N in our case, correct. What will this index be? D 0. If D0 is not equal to null, then you make that as the output, that is the E0, because K is also set to 0, okay, right, K is equal to 0. See this, that is the instruction. K is 0, J is 0, okay, right. So, and K0 is also 0. Why is K0 0? Because there is the first RV, RV 0, correct. Why is J 0? Because you set it to 0. Why is this? Mod NCB is a circular buffer, okay, right. If this bit is not equal to null, then you make that as output. What will this output? E0, right. So, you increase this, what is the K becomes 1, right. Go back, because this is this if, because this while has not ended. So, what happens here? Then this is end if, okay. You come here, J is equal to, what becomes, what is the value of J now? J becomes 1, correct. K has become 1, J has become 1. You will see the use of this K and J, okay. I will show you that immediately, okay. This while has not ended, okay. And what is happening here? You see this, come back here, J, what is the value of J? 1. And what is the value of K? That is also 1. So, J is basically, you read this, come here, J is the input index and K is the output index. Where is K being used? To store into the output buffer. J is being used to read from the input buffer, fine. So, come here, you look at this, if J is 1 now, K naught is always 0 because there is RV 0. So, forget about that, they will always be set to 0, okay. Now, if D1 is, let us say null, okay, just for example, What will happen? Then you come here. You will not write that bit into the output buffer. So K index doesn't get increased. It's only the J index which is getting increased. Right? Okay, that's how this rate matching is removing the null bits. Okay, so the J input index has increased, you go to the next one. Because K is only 1 as of now. Right? You have read only 1 bit. Means you have written only 1 bit. Okay. Now what happens to the J index? It becomes 2. If D2 is again null, you again skip this. Come here. Okay, J becomes 3. K is only 1 as of now, because these 2 bits were null, you have not recorded them in the output buffer. Correct? Okay. If you don't hit the null bits, then J and K will be same. If you hit the null bits, input index will be different from the output index, because you have to skip those input bits. Okay. What are those input bits? Those input bits which are written in the rate matching buffer. Correct? Okay. So what is this rate matching module doing? Okay, look at this. It is reading from the circular buffer and writing into some other buffer which is denoted as E. Correct? That's what we saw. That it reads from a larger size buffer, writes into a smaller buffer whose length is E. Do we understand this? Okay. Right? That's how it is implemented. Okay. And this is a circular buffering part. So this is like one part of it. Another part of it, because I have to show you this, it's a little more sophisticated, because it is, if you read this is like this, it continues. Okay, I'll show you why this is there, but we have not understood that part of the standard, so I'll just skip it and show you what it has to calculate this E also, right? Who is going to calculate the E? Rate matcher only. Okay, so this is actually that for each of this module, each of the coded block is going to calculate how many bits it can transmit, basically the value of E. Right? That also needs to be done. Who is going to do that? And that's what it is. Okay. I'll skip all of this. Okay, because I have not taught you. Okay. What is this telling you? It is basically it has to calculate E. Okay, denoting the ER, the rate matching output sequence for the rth code block, where the value of ER is determined as follows. Okay, all these instructions, they are only there to calculate the value of E. Okay, and it has to take care of like MIMO, it has to take care of certain other things also which I have not even taught you. Okay, but so for each of this code block, R is equal to 0 to C minus 1. Okay, right, this needs to be calculated. Okay, correct. What's happening here then? So look at this. Okay, so what is this instruction telling you? If this particular coded block is not scheduled, okay, transmitter has not scheduled this coded block, set ER as 0, because this code block is not allowed to be transmitted. Okay, otherwise, depending on certain conditions, I'm not going to talk about these conditions because I have not taught you. Okay, what I am going to show you here is, okay, if you ignore all this floor and seal here, what is happening here? NL, QM, they get cancelled. If I just ignore the floor and the seal operation here, okay, this is flooring operation, this is the sealing operation here. Okay, right? What happens? NL, QM cancels NL, QM. What is the value of G you are getting? G by C. Okay, right? So this is only the E value calculation. And why this? What is this NL? NL is the number of parallel MIMO layers you can transmit. I'm not going to get into the detail of that because I have not even taught you that. Okay, right? QM is the modulation order. Okay, so this E calculation differs based on this, the number of layers and the modulation order. Okay, so that's what it is. But for our study, what is happening here is NL, QM, they cancel each other. Okay, and E becomes G by C, and that's what I have taught you. Number of bits which each module can, each of this, which are allowed to be transmitted for each of this coded block. That is G by C. Fine. So this is what it is. NL is the number of transmission layer that the transport block is mapped into NL. For us, it is NL is 1. Okay, right? Q is the modulation order. So if whatever is the modulation order, okay, you put it over here, gets cancelled, because this conditions come on based on this certain other requirement which I have not taught you, right? So as I said, this is only E calculation. That's what it is. So G is the total number of coded bits available for transmission of the transmit of the transport block. G is what? Total number of bits. E is G by C, right? Okay, and this is, you can forget it because it was there in the standard. I have left it for you. Okay, if CB GTI is not present in the DCI scheduling, the transport block, and C dash is the number of scheduled blocks. I am not going to talk about it because I have not taught you what is DCI. I have not taught you CB GTI, what is it. I have not taught you number of transmission layers. Okay, but I had to tell you about rate matching module, and that's a part of it. Okay, right? If you don't understand this, if you simply fit in this, E comes as G by C. That's what is our requirement. That's the key takeaway from this part of the standard. Okay, what was required for us is this, but E has also needs to be calculated. Okay, so I'll stop here and then we'll continue in the next class. So this is basically what we have learned in these two lectures is how rate matching is designed and what is the need of rate matching. That's what we have learned. Okay, thank you.